Hi, my name is Pedro Gonzalez and I'm the project manager of the Arecibo Observatory Radiation Pattern Measuring Drone. With me are Fernando Davis, Cesar Delgado, Veronica Rivera, and Orlando Ramos, and we'll be presenting our latest progress on the project. The Arecibo Observatory was the second largest radio telescope in the world up until December 1, 2020. It had a 1,000 diameter reflected dish built out of 35,000 aluminum panels of 3 by 6 feet that captured and redirected the electromagnetic waves to the antenna above the dish. Experiments using the radio telescope as a tool took time, money, and effort, and the data was only processed after the experiment was concluded, meaning that if the equipment was faulty, the corrupted data was not salvageable, costing valuable resources. To determine the condition of an antenna, its radiation pattern must be measured. The traditional methods to measure the radiation pattern is using an anechoic chamber. Due to the dimensions of the Arecibo Observatory, conducting the required measurements through traditional method is not feasible. A collaborative research project between MIT Lincoln Labs, Arecibo Observatory, and the University of Puerto Rico Mayagüez campus was created to use an unmanned aerial vehicle to measure the irradiated pattern by modifying a pre-existing flying drone equipped with data logging capabilities. Due to the collapse of the Arecibo Observatory, a new measuring site is required. Even though the measurements will not be conducted in Arecibo Observatory, there will be any changes in the data collection process, and with a few modifications of the matching circuit of the receiving antenna, we will be able to continue with the project.
The interconnection of our system environment starts with two 22.2 volt batteries, where each battery will be connected to a DC-DC buck converter circuit. This circuit will step down the voltage to 5 volts, and the circuit will be supplying power to the USB hub and the SBC. The USB hub acts as a power distributor for our subsystems, powering some of our most important components. At the same time, the USB hub will manage the data throughout the grid, sending said data obtained from flight through a series of steps before reaching the SBC as real, computable, and tangible information.
The steps are as follows. Before getting to the SBC, the signal is first received by a microstrip Mendel antenna, which will receive the balanced signal from the WDA. The signal will pass through the matching circuit, which is in charge of unbalancing the received signal and matching the system impedances to avoid signal reflection and achieve maximum power transfer. Then, the signal will go through the up converters, which will increase the signal frequency for one that the SDR can detect. The SDR is able to detect frequencies of 70 MHz minimum, so the up converters will up the passing frequency by 125 MHz. In this case, there will be a total of 130.125 MHz that will be passing through the SDR. The SBC contains code written in Python designed to speak directly to the RTK GPS and UAV GPS. By knowing the exact location of the UAV at all times during the flight, we can establish a set of waypoints in which the unit will gather the signal data. In addition, the SBC takes SDR input and transforms it into a binary file, which we can then store in an SD card. We'll talk more about the binary data later.
The DJI Matrice 300 RTK has some features that fit perfectly with our project. This drone has a payload capacity of 5.95 pounds and a maximum flight capacity of 55 minutes, and it can be used with an existing application that was developed also by DJI, which enables us to create and save a flight plan given the location of the waypoints. The drone also comes with obstacle avoidance technology, which can aid in case of any flight emergency, as well as a return to home feature.
Hi, my name is Orlando Ramos, and I will be talking about the details of the antenna. To measure the radiation pattern of the AO heating facility, an MMA with a matching circuit was designed and assembled to measure the specific signal of 5 MHz, circularly polarized. The conductor was folded to make the overall length shorter, and it was laid out on top of a flat 9x9 FR4 substrate. The main motivation of the MMA selection was because of the small antenna theory, which indicates that any small antenna can be paired with any frequency using a matching circuit. The first component of the matching circuit must be balloon transformer, which will transform the balanced signal to unbalanced to be able to pass the signal to the SMA cables that will connect the matching circuit with the SDR. Then, the signal will pass through an LC matching circuit that will match the impedance at 50 ohms, ensuring a maximum power transfer and avoiding any signal reflections. The SDR is able to process signals from 70 MHz to 6 GHz. For this reason, the final component of the matching circuit are the O converters, which will elevate the signal frequency from 5 to 130 MHz. As mentioned, the signal will be passing through SMA cables, which have an impedance of 50 ohms, which is not matched with the source impedance. An LC matching circuit was implemented to be able to match the load impedance with the source impedance and obtain maximum power transfer. It was decided this type of LC configuration to protect the system from high frequencies, as the capacitor behaves as an open circuit in high frequencies and will not let the high frequency signal pass through the rest of the system. Tests were performed to verify the impedance of the antenna and the return loss of the components. Expected impedance was 50 ohms and the result in both polarizations and frequencies was about 49 ohms. The return loss expected was about 50 decibels and the result obtained for both polarizations and frequencies was about 43 decibels. There are margins of error, but we concluded that the antenna's components are serving their purpose.
After receiving the output binary data from the SDR, the Python script parses it and creates a file with the complex values and the UPS data. This is then passed on to the MATLAB script, which performs a near-field to far-field algorithm to calculate the average of each complex value in each location and the magnitude and phase for those averages.
The next step for the project is the integration, making sure that the drone can fly, carry our system, and follow the given waypoints while capturing the data in each one. We must conduct some tests to make sure that the data collection system is working efficiently by being able to capture the data in each waypoint that is given and return to home with clear measurements of the radiation pattern.